Hello and welcome to the lecture on ultrasound contrast agents. I am Professor Himanshu Shekhar. So far, as you have been learning in this course in ultrasound, ultrasound has several advantages. It is getting faster, better and cheaper as technology progresses, and it has several applications. So for example, here you are able to see the hand of a fetus in an ultrasound image. This is the opening and closing of heart valves as seen in two-dimensional and three-dimensional ultrasound. So here are the two-dimensional images, and here is the three-dimensional ultrasound image. And here is the 3D, and actually it's a 4D because this is a picture, but it can also be done in which you can see the live video of the fetus. You can see things like a fetus sucking on his thumb or even smiling. And so these are some excellent applications of the latest generation state-of-the-art ultrasound techniques. But ultrasound falters when it comes to imaging blood-filled or vascular organs. And the reason is because the backscatter from blood is not very strong. The blood is mostly liquid, it only has few formed elements, and because of which there is not a very strong signal from the blood. Now, there is a workaround, of course. There is Doppler ultrasound, which is well established, and this Doppler ultrasound, which you will learn about in more detail in a future lecture. Doppler ultrasound provides anatomical as well as flow information. So you can see the location of regions which have flow going on, and you can also measure the flow speeds and the direction of flow using Doppler. However, the challenge is Doppler ultrasound relies on shift in frequencies because of the Doppler effect. Now, the shift in frequency is proportional to the motion of the velocity of the scatterer that is moving. So this could be a red blood cell, for example. However, if there is slow flow, or there might be cases where you have an organ filled with fluid and there isn't much flow, there could also be low volume flow. In such cases, it is hard to detect the target using Doppler effect. So for example, consider the microcirculation. These microcirculation have very low blood flow velocities, and Doppler cannot sensitively detect the blood flow in the microcirculation and cannot even anatomically look at the microcirculation. So that is where there is a need for ultrasound contrast agents to enhance the scattering from blood-filled organs. So let's delve into the history of ultrasound contrast agents. It was Dr. Raymond Gramiak, one of the early pioneers in contrast agents at the University of Rochester, who discovered part of this by accident. He was injecting indocyanine green dye into the heart. This is a contrast agent, a dye for X-ray angiography. So what this does is, here is an example of an X-ray angiogram. As you put the dye, then it fills up the blood vessels which are on the heart, and you are able to visualize these blood vessels. Now, it turns out that he was also imaging with ultrasound, and as he was imaging with ultrasound, when he injected this indocyanine green dye, he also saw an increase in the ultrasound signal, and he was very surprised. He thought that there was something about this indocyanine green dye which also helps increase the ultrasound signal, and therefore it could be an ultrasound contrast agent as well. However, it was later found that the microbubbles formed at the catheter tip as the dye was injected was the real reason behind this contrast enhancement, and that is where the first generation contrast agents began. There were many other early contributors to the development of ultrasound contrast agents, but let us discuss this saline contrast agent. To create this saline contrast agent, the clinician would agitate saline so that microbubbles are formed, and it is still used today in visualizing the right side of the heart. There is an atrial septal defect, which is an abnormal opening in the dividing wall between the atrial heart chambers. Now the problem with this defect is it causes a connection between the arterial and venous sides, and the venous debris can actually go to the arterial side, and it can cause embolism or the blockage of blood vessels, which can be serious. So this has to be detected and surgically repaired. Now, to detect this atrial septal defect, what is done is you inject the saline contrast agent in one of the atrial chambers, but if the contrast agent appears in the other chamber, that would mean that there is actually a hole which connects the two chambers, and that is how it would be diagnosed, and then it would be repaired using surgery. Now, this is a great application of this simple technology, but if it comes to imaging other vascular organs in the body, there is a problem with saline contrast agent. It dissolves very quickly, and it also cannot pass through the circulation of the lungs. Therefore, there was a need to develop a new generation of contrast agent which was more stable so that it could be used for other vascular organs. So, here is an example of a commercial lipid shell contrast agent. So, that is where a shell comes into picture to stabilize the contrast agent, and this example is called SonoView. It is approved in both US and UK and also available in India, and it is filled with sulfur hexafluoride gas. It is a very heavy gas. You may have seen some demonstrations where the speaker inhales sulfur hexafluoride gas or the speaker inhales helium. When the speaker inhales helium, it is not a dense gas, it is a very light gas, and because of which the speech of the speaker becomes very shrill and like Donald Duck like. And you may also have seen when the speaker inhales sulfur hexafluoride, the voice becomes very heavy, pitched and deep. And that is because sulfur hexafluoride is a very heavy and dense gas. So, what is the role of sulfur hexafluoride here? It is a heavy gas and it is also sparingly soluble in aqueous media. So, therefore, the bubbles which are filled with sulfur hexafluoride gas are more stable than air bubbles. And similarly, when you have a shell on the bubble, it enhances the lifetime of the microbubble. So, here is a schematic. You have the gas inside and you have a lipid monolayer shell which stabilizes this bubble. So, there are other contrast agents which are commercially approved as well, and some of them are ones with protein shell, for example Optison. There are other phospholipid shell contrast agents as well, which include Definity, and these are approved in different countries for clinical use. Now, these contrast agents are vascular contrast agents, so they stay within the blood system. Now, this is different compared to contrast agents of other modalities. For example, in MRI you may have gadolinium based contrast agents. In CT X-ray you may have barium or iodine based contrast agents. Those contrast agents leak into the interstitial space, but here these contrast agents are actually given by injection either intravenously or using a catheter, and like I mentioned, they are stabilized by phospholipids or proteins. There are polymer shell bubbles also in research, but to my knowledge they are not clinically approved. These have low solubility gas filled in them, such as sulfur hexafluoride or some perfluorocarbon gases which have low diffusibility, low solubility in aqueous media, and therefore they stabilize the microbubble. Now, when you fire ultrasound on these microbubbles, they undergo volume pulsation. I will show more examples. And this is a type of contrast agent where you can get rid of the contrast from your region of interest at will by destroying them by using higher acoustic pressures, which will pop the bubbles and get rid of the contrast agent at will. So, it is very flexible, and the safety profile is well established because these contrast agents have been used for more than 20 years, and tens of thousands of exams have been done in different countries. So, why is this microbubble a good contrast agent? Different compounds in MRI or in CT are used, and that is because of the physical mechanisms by which the contrast agent interacts with the radiation that is being used for imaging. Now, in this case, when it comes to interaction of microbubbles and contrast agents, microbubbles are highly compressible, and they also, being filled with gas, have low density and low speed of sound in the gas, and because of which the acoustic impedance of these microbubbles is low compared to the surrounding media, and therefore there is a high impedance mismatch and a strong backscatter. Further, there is a resonance phenomena. Microbubbles are not just passive scatterers, but they actively re-radiate the sound because of a resonance phenomena, which we will discuss further, and they give out acoustic signatures that are vastly different from tissue. So, this is of great importance Because of these unique acoustic signatures, we can differentiate between the bubble signals and the background tissue signals, which helps us improve the contrast and the sensitivity of imaging. So how do we produce bubbles? I am sure all of you have made your own bubbles. You take some liquid, you add a surfactant to it, and you agitate it. That's the most basic principle of making a bubble. Now it turns out, if you make such bubbles, they are large in size. They may be millimeters to centimeters in size. If you want to make bubbles that are micrometers in size, smaller than the size of the red blood cell, for example, which is important for the safety, then you would have to go for a high shear mixing. And here we either create a solution with either proteins or lipid, which are in the form of liposomes, and then we agitate it either mechanically at very high speeds, or we agitate them by ultrasonication at kilohertz frequencies. And we have a lipid gas interface or a gas protein interface. So when you provide energy at that interface, it leads to the encapsulation of gas, and these microbubbles are formed. Now these methods produce a polydispersed size distribution. By that I mean that you won't have microbubbles of a single size, but you will have a range of sizes present in your formulation. Now that is good and bad. That is good in the sense that it will be sensitive to a range of frequencies, but it will not be adequately, or it will not be sharply sensitive to a particular frequency. So that is where some researchers are also investigating methods to develop monodispersed bubbles, which have bubbles which are mostly of a single size, and then they are highly sensitive to the resonance frequency. And to make these kind of bubbles, a variety of techniques have been reported. There have been techniques which filter traditionally made bubbles, as well as microfluidic techniques which can make highly monodispersed bubbles. But the challenge is these techniques are slow, and the bubbles made are relatively less stable compared to the traditional techniques. So this is still under research, and this is a promising area of inquiry. But nonetheless, what you can see is that these bubbles can be made using a range of methods and can be applied for applications in contrast enhanced imaging. Now if you are going to inject these bubbles into the body, they ought to be stable, and the stability is brought about by the gas as well as the shell. So the shell typically uses a surfactant. This surfactant can be lipid or a protein, and it also has a spacer molecule which is typically polyethylene glycol based. So one example can be PEG 2000 stearate, and this spacer molecule actually helps to keep the bubbles away from each other so that there is no agglomeration of bubbles. And the shell surfactant reduces the interfacial tension. So you may be aware of surface tension, and you may be aware that the bubbles actually dissolve because of the high surface tension. So by reducing the interfacial tension, and also the membrane, which is the surfactant on the surface, also reduces gas diffusion, and through this mechanism, it is able to increase the lifetime of these bubbles. Now once you make these bubbles, if you store them in airtight vials in a gas saturated fluid, so the fluid will be saturated in the same gas that is contained in the microbubble, and you probably add some thickening agent so that the gas diffusion is slowed down. You can store it at refrigerated temperatures, typically about 4 to 5 degrees, which will again slow down gas diffusion. So now these bubbles will be stable for years typically inside the vial. However, when you put them in static air saturated fluid, then they last for tens of minutes. Could be anything between, say the half-life could be anything between tens of minutes to an hour. And when you inject them in the body, it is a more harsh environment. There is a pulsation, blood pressure, high flow speeds in certain regions. So in the body, the half-life is few minutes, and typically once the agent is injected, after some time, the gases are exhaled out of the body. A very small volume of gases in microliters goes into the body, and then this is exhaled out through the lung. the shell gets metabolized, broken down and cleared by the kidney, liver and other tissues. So now let us discuss microbubble ultrasound interaction physics in more detail. You may be familiar with this harmonic oscillator or a spring mass system where you have a mass, you are applying an external force, it could be a sinusoidal force, and because of this force, this mass is oscillating. Now note that the spring has a spring constant of K, so it resists this oscillation, it provides a certain stiffness, and there is a mass m. Now consider a bubble which is oscillating under applied external pressure, which is coming from ultrasound in this case. The bubble is oscillating in some kind of liquid media. So as it is oscillating, it is displacing the liquid. So it is doing work against that mass, right? So it is analogous to the mass here in the spring mass model. When you compress the bubble, then you also compress the gas which is inside the bubble. And when you stretch the bubble, when you expand the bubble, you rarefy the gas in there. So there is a certain stiffness or a spring constant of the gas, which is analogous to this harmonic oscillator. And when it comes to the ultrasound pressure, which is also a sinusoidally varying pressure typically, this is analogous to the sinusoidal force which is applied in the spring mass system. So now we understand the physics of the spring mass system pretty well. So we can also derive some formulation for the physics of oscillating gas bubbles in response to ultrasound. So the most common model that has been extensively researched over several decades is the Rayleigh-Plesset model, and several variations and modifications of this model have been published. This is a nonlinear second order ordinary differential equation which is derived from the Navier-Stokes equation assuming spherical symmetry. So this would be a bubble in an infinite medium and it is being exposed to ultrasound. So this is the equation of the Rayleigh-Plesset equation. What you are seeing here is that this defines the time dependent radial oscillation. So R is the instantaneous radius of this bubble, and the radial oscillations can be solved by solving this model numerically. So rho refers to the density here. These dots refer to derivatives. So R double dot is the second derivative, R dot is the first derivative. P naught is the ambient pressure. So this will be the pressure outside the bubble, and if the bubble is submerged, then it will be the sum of the atmospheric pressure and the hydrostatic pressure. Then sigma here is the surface tension, PV is the vapor pressure, R naught is the initial radius or the equilibrium radius, kappa is the polytropic exponent. So if you recall from thermodynamics, we say PV to the power kappa is constant, that kappa is the polytropic exponent, and PT is the excitation pressure of the ultrasound. Mu is the viscosity of the surrounding fluid. So this is the Rayleigh-Plesset equation for an unshelled bubble. If you introduce a shell, then few other terms will be added. Now solving this model, you are able to get the time dependent radial oscillations of this microbubble. We can also get the pressure from those radial oscillations by using this equation. So if you want to calculate the pressure radiated at a particular distance, you can solve for this expression. Now this Rayleigh-Plesset equation is highly nonlinear and is quite complicated. So we can get some intuitive understanding by applying some simplification. So if we go for linearization, if we assume that the bubble oscillations are really small, then we can go for some linearization. And we can also ignore the contribution of viscosity, vapor pressure and surface tension. So then we get this equation which is called the Minard's equation. This equation relates the resonant frequency f to the radius of the bubble, and then there are constants of pi, gamma which is the adiabatic index, P naught is the ambient pressure and rho is the density. Now let us discuss the resonance behavior of these microbubbles. So as you can see here, I have plotted the linearized resonant frequency of these microbubbles. On the x-axis is the radius of the microbubble, and on the y-axis is the resonant frequency in megahertz. The radius is given in micrometers. So now, if I want a bubble that would resonate at about 10 megahertz, then you can see that the resonant radius would be about 0.5 microns, slightly less. Similarly, if I want a bubble to resonate at about 4 megahertz, then the resonant radius would be probably about 0.8 micrometers, closer to 1 micrometer. So this inverse relationship holds. Now this is a simple Minard's equation with several simplifications, but as it turns out, not only the microbubble radius or diameter, but the shell properties. In case of shelled bubbles, the shell viscosity, the shell stiffness, they also play a role in the resonance frequencies. The gas properties, for example, if I fill a bubble with air versus I fill it with a heavy gas such as sulfur hexafluoride. Typically, the polytropic index of the gas matters as well. Then the acoustic pressure. So it turns out if we go for the exact solution of this Rayleigh-Plesset equation and not just this linearized model, the acoustic pressure also plays a role in determining the resonant frequency. And of course, the bubble is oscillating in a fluid where the density of the fluid and the viscosity of the fluid will also matter in determining the resonant behavior of the microbubble. Now let's discuss the scattering cross section. It is a measure of the strength of the bubble scatter. So sigma SC is the scattering cross section. It quantifies the total power of the scattered ultrasound relative to the intensity of the incident ultrasound wave. And sigma SC is given by this expression. So R naught is the equilibrium or the initial radius of the microbubble, and omega naught is the resonant frequency, and omega is the frequency, and delta is the damping, and delta total stands for the total damping. So let me explain here. What is this damping? When the bubble oscillates, damping refers to the loss of energy in the bubble, and this can happen because of radiation from the bubble, radiation of sound. This is not ionizing radiation, by the way, so don't confuse it with X-ray or nuclear radiation. There's also some viscous damping because of, it is analogous to friction, losing energy because of this viscosity. And if there's a shell, there's also shell friction damping. So there are two types of damping. One is because of the viscosity of the fluid. The other one is because of the shell friction. Now, if you sum all of this, then this is the total damping. Now it turns out when we are at resonance, so omega naught by omega will become 1, and the denominator will lose the first term here, only delta square total term will remain. So in other words, the scattering cross section will increase sharply. So at resonance, the scattering cross section is limited only by damping. And you have seen something similar. Probably if you have learned about circuits, then you know that when an inductor capacitor resistor circuit is at resonance, then the inductive and capacitive impedances cancel each other and only the resistive component remains. So it is pretty similar here, where only the total damping limits the scattering cross section, and typically at resonance the scattering cross section can increase by orders of magnitude relative to being off resonance. Now to characterize our microbubbles, what do we need to do? So the microbubble size is an important parameter and it's a determinant of its acoustic properties as well. So we would like to measure the size distribution experimentally, and this is where a technique of electrozone sensing or impedance sensing is used. Typically if you measure these bubbles using light scattering, because these bubbles have unknown refractive index, sometimes it can cause artifacts. Therefore, impedance sensing is considered the gold standard for imaging microbubble size, and that is where you have an electrode and you have a microfluidic channel through which a bubble is passing. So when a bubble passes, there is a change in impedance because the fluid is displaced by the bubble, and there is a change in impedance which is then related to the microbubble size. So here's a picture of a cuvette in which you would put your bubble suspension, which is sufficiently dilute, and you would have this aperture through which you would perform electrozone sensing. So these are measurements that span from about 400 nanometer all the way to 15 micrometers, and here we are showing only till about 6 micrometers because there aren't many bubbles beyond this size. So you can see that the distribution is of log normal type shape, and it is somewhat polydisperse. Now to characterize the acoustic properties of the bubbles, there are different techniques. We can measure the scatter from the bubbles. We can also measure attenuation, and that is where this technique of attenuation spectroscopy comes into picture, in which you have typically two transducers which are confocal and facing each other. Typically broadband PVDF transducers are used. PVDF is a membrane, it's a piezoelectric material, and it has a broad bandwidth. So what you can do is you dilute the bubble suspension and you put it in an acoustically transparent chamber in the beam between the transmission transducer and the receiving transducer, and then you can measure attenuation as a function of frequency. So in this case, we have measured the attenuation coefficient as a function of frequency for SonoView, and in this case what we are seeing is that the resonant frequency is closer to about 3 megahertz, because that is where the highest attenuation exists, and we have done some measurements versus time. So we have gone as far as 1 hour 30 minutes. We don't see a very strong change in the attenuation coefficient in this time period, showing how stable these bubbles are in the static aqueous solution. So let me summarize. In this lecture, we discussed about the need for contrast agents in ultrasound to visualize blood-filled organs. We discussed why microbubbles are an excellent contrast agent for applications in ultrasound. We discussed how we can fabricate these microbubbles, how they are stabilized, and how they are cleared out from the body, which is an important consideration for safety. We discussed bubble dynamics in response to ultrasound, although in a simplified manner. We discussed the Rayleigh-Plesset equation, and we also discussed the linearized or the approximate resonance frequency of the bubble. And lastly, we discussed experimental techniques for characterizing these bubbles, which include size and attenuation measurements. So I hope this gives you a good idea about ultrasound contrast agents, and in the next lecture, we will be discussing imaging techniques, essentially contrast enhanced imaging techniques for imaging blood flow. And okay, so in the next lecture, we will be discussing contrast enhanced imaging, or how these microbubbles can be used for imaging vascular organs. I hope you enjoyed this lecture. See you in the next lecture. Thank you.